Today we're going to talk about solving homogeneous differential equations with constant coefficients. We're going to be interested in what happens when the order of the differential equation is greater than 2. In order to do that, we're going to take a quick detour first to talk more about polynomials. And for now, I'm using z as a variable to kind of indicate that we're talking about a polynomial over the complex numbers. So we're allowing z to be a complex number. And for right now, the coefficients, an minus 1, etc., up to a naught, those can be complex numbers as well. And just by convention, we're going to assume that a sub n is not equal to 0, so that this will be an nth degree polynomial. Now, we've already talked about the fundamental theorem of algebra, what I'll just write as the FTA, the fundamental theorem of algebra, that says any polynomial of degree greater than or equal to 1, so any non-constant polynomial, has a root. This is over the complex numbers, a root over c. And the consequences of this are enormous. The fact that a polynomial, an nth degree polynomial, has one root means we can take this polynomial, find one root, say r1 is a root, then we can just factor out this linear factor z minus r1 from the polynomial, and what will be left will be an n minus first degree polynomial. And then that will have a root, say r2, and we can factor that out. And we can keep going until we get down to a constant, say the constant a sub n. In fact, here, since all of these have these are all monic polynomials, z minus r1, z minus r2, etc., you'll see there's just 1 times z to the n here, so we know that at the end we'll be left with a constant a sub n, the lead coefficient. So any polynomial over the complex numbers factors completely with complex roots. Now, of course, some of these roots, r1, r2, up to rn, might equal each other. There's nothing that says these roots have to be distinct. They could all be exactly the same. You could have an nth degree polynomial which has only a single root with multiplicity n, or it can have n distinct roots, or it could have two. It could have one root of multiplicity 2 and others that are distinct. Any possibility here for any number of these being equal to any others is still a possibility, but we know the polynomial factors completely. What I want to talk about is a very special situation now, and this will be relevant to us when we're solving real differential equations. If we have a polynomial, and we're still thinking of this as a polynomial over the complex numbers, so z can be a complex number, but if these coefficients happen to all be real numbers, so a naught through an are all real numbers, so it's a special complex polynomial which just happens to have real coefficients, then there's a very special property that happens with the roots. Anytime you have a root r, then you'll also have a root r bar, the complex conjugate of r. So if r is, say, x plus iy, r bar here, the complex conjugate, is x minus iy, and whenever this is a root, then this is also a root. Of course, this is true if r is a real number, but then r bar is the conjugate of r is exactly the same as r, so the theorem doesn't really tell you anything new. But what this does tell you is if the coefficients of a complex polynomial are real, then you can have real roots. That's certainly a possibility. When you have non-real roots, they come in conjugate pairs. Anytime you have a root r, you have the corresponding root r bar, its complex conjugate. Once you segregate those two roots off the side, you can keep going and you have other conjugate pairs of non-real roots. That's a possibility. But it gives you a great sort of structure to what the roots look like. And I want to show you really why this is true. It's a very simple and elegant argument for why it's true that if the number r, a complex number, is a root, then its complex conjugate is also a root. The reason that's true is because complex conjugation works very nicely with multiplication. In other words, if we have w times z, and we take the complex conjugate of that, that's the same as the complex conjugate of w times the complex conjugate of z. That might not be totally obvious given the way conjugation works, but just try it. If z, say, is x plus, I shouldn't use that notation. Let's say that if z is a plus ib and w is c plus id, check this. Try to compute each side, and you'll see that this is true. What that tells us when we just use that over and over again is that if we want the complex conjugate of z squared, that's the same as taking the complex conjugate of z and squaring it. If we want the complex conjugate of z cubed, that's the same as taking the conjugate of z and cubing it, etc. So the nth power for any positive integer n, the conjugate of the nth power is just z bar to the nth power of the conjugate. And since it's also true, and I didn't mention this, but this is pretty obvious, you can probably check this just in your heads, that the complex conjugate of a sum is just the sum of the complex conjugates. If we have a polynomial of this form, if p of z is an z to the n plus an minus 1 z to the n minus 1, all the way down to a1z plus a naught, with the a's real, and if r is a root, well, that tells me, since r is a root, that a sub n r to the n plus an minus 1 r to the n minus 1 all the way up to a1r plus a naught equals 0. If I take conjugates of both sides, the conjugate of 0 is just 0. If I take the complex conjugate of the left side, I get the conjugate of a sub n times the conjugate of r to the n. But if the a's are all real, the conjugate of a sub n is just a sub n, and the conjugate of r to the n, remember, is the conjugate of r to the nth power. And we do that for each term, an minus 1, which is a real number, and then we'll have the complex conjugate of r to the n minus first power, and we keep going up to a1 r bar plus a naught. So here I'll just write we conjugate both sides here. But what does this statement say? This tells me p of r bar equals 0. This is exactly what you get when you plug r bar into the polynomial p. In other words, this is p of r. Here, saying r is a root means p of r is 0, but that tells you p of r bar is 0, and that's exactly what we wanted to show. Whenever r is a root, so is its conjugate, r bar. And thus, complex roots of polynomials with real coefficients come in conjugate pairs. Now you might wonder, why would we care about that? Well, we already saw that that was really important even when the characteristic polynomial of we were looking at the characteristic polynomial of a second order linear, homogeneous, constant coefficient differential equation, because then the characteristic equation was just a second degree polynomial, quadratic with real coefficients, and we did, in fact, need the fact that when the roots are complex, they come in conjugate pairs. We didn't need a theorem like this to deduce that. We just had the quadratic formula. But what this theorem here tells us is that the same idea that complex roots come in conjugate pairs works for higher order polynomials just as well as for quadratics. One should note that when you have a conjugate pair of roots, r and r bar, when you multiply these linear factors, z minus r and z minus r bar, you just, the same basic rules apply. Notice that r plus r bar, when you add a number and its complex conjugate, if r is a plus ib and r bar is then a minus ib, then r plus r bar is just 2a. That's twice the real part of r. That's what the 2a is here. And so when you multiply these two linear factors together, when these constants r and r bar are conjugates, you'll get something here which is a quadratic with real coefficients. When we put all of these results together, this with the fundamental theorem of algebra, what does that tell us about factoring a polynomial? If you start with a polynomial, we're talking about a complex polynomial, but which has real coefficients, you can factor it according to the fundamental theorem of algebra into n linear factors, not necessarily distinct, but n linear factors times some constant. This would be the lead coefficient there, but all the rest are just these simple linear factors. Now, for this use, I'm just going to kind of use the notation in a slightly different way. There'll be some real roots. Let's say all of these r's, we'll call these the real roots of the polynomial, but there will be some complex roots. So the s's, that looks silly, but the s's are non-real, meaning they're complex numbers which are not real numbers. They have non-zero imaginary part. And for those non-real roots, when you have one of those, it will come along with its complex conjugate as another one. So those will come in conjugate pairs. So when you factor the polynomial, you'll have a pair of linear factors for each conjugate pair of roots. And here I'm just choosing indices k and m. K will denote the number of real roots, the number of linear factors which correspond to the real roots, and m will correspond to the number of conjugate pairs of roots. Now again, I'll remind you that these real roots don't have to be distinct from each other. They could have various multiplicities, and even these conjugate roots, S and S1 and S1 bar might be the same as S3 and S3 bar. You could have conjugate pairs of higher multiplicities as well. But in the end, we can factor things like this. What's the consequence of that for solving higher order homogeneous linear constant coefficient differential equations? It's always a mouthful to say this. I've been doing that a lot over the last couple of weeks. So let's just get back to our standard notation from the book. We'll take our differential operator L of y to be a naught times the nth derivative of y plus a1 times the n minus first derivative, all the way up to a sub n minus 1 y prime plus a sub n y. By convention in our book, and what we're actually doing trying to solve these differential equations, is we're trying to solve real differential equations. So here all of the a's are real. Now that doesn't mean we're not going to be interested in complex solutions later, but we'll have the homogeneous differential equation, L of y equals 0, is an honest-to-goodness real differential equation, and in the end we're looking for real functions that are solutions. Well, there'll be a characteristic equation for this homogeneous differential equation, and that characteristic equation will be some nth degree polynomial. We could write it at first, just based on the form of L here, we could write the characteristic equation as a naught, and I'm going to use z as our variable instead of r the way the book does, because that'll be a little bit nicer in this context. The characteristic equation will be a naught z to the n plus a1 z to the n minus 1 up to a n minus 1 z plus a naught equals 0. So here I'm writing the characteristic equation, again using z instead of r. It doesn't matter, it just looks nicer here. It's an nth degree polynomial equation. And we can factor this nth degree polynomial on the left in exactly the way we did before. And I'm going to, just by the notation I'm using, I'm going to choose the r's to be real and the s's to be non-real complex numbers. Well, the exact same argument we've talked about before tells us anytime we have a root, for example, R1, or let me say this, anytime we have a root of the characteristic equation, that means e to that number times t will be a solution to our differential equation. The argument is identical to the one we've seen before. So that tells me that what e to the R1t is a solution to the differential equation L of y equals 0, since R1 is a root. And the same will be true for e to the R2t through e to the rkt. We'll have all of these solutions, which are just regular old exponential functions, e to a real constant times t, and those will all be solutions to our homogeneous differential equation. But we'll have other solutions based on these complex numbers. So let's say S1 is lambda 1 plus mu 1 I, S2 is lambda 2 plus mu 2 I, all the way up to S sub m, which is lambda m plus mu m I. Then we also have solutions. So here we have solutions. We also have solutions for each of these, say corresponding to having S1 and S bar and S1 bar be roots. That's lambda 1 plus mu 1 I and lambda 1 minus mu 1 I are both solutions. We know from work we've done earlier that e to the S1t and e to the S1 bar t will be solutions, but those will be complex. And using the same trick we did before, taking the sum of these solutions and dividing by 2, we'll have a solution that looks like e to the lambda 1t cosine mu 1t, and by taking the sum of those two solutions, the difference and dividing by 2i, we'll get the solution that looks like e to the lambda 1t sine mu 1t. These will be honest to goodness solutions of our homogeneous differential equation. And that the same will be true for S2 through Sm. So we'll have e to the lambda 2t cosine mu 2t, e to the lambda 2t sine mu 2t, all the way up through e to the lambda mt cosine mu sub mt, and e to the what is it? E to the lambda mt sine of mu sub mt. Now here's the problem. If there were repeated roots, then this isn't a total of k distinct solutions. If R1 had multiplicity 2, say R1 and R2 were both the same, these might be the same solution. So when there's a multiplicity, if R is, say, a real number, a real root of multiplicity, I don't know, we need some extra number here for that. Let's say it's of multiplicity p, that, not p, we've been using p already. I'll just say multiplicity j. Then it's true that we have e to the rt is a solution, but so is t e to the rt, and so is t squared e to the rt, all the way up to t to the j minus 1 e to the rt. So if you have a root of multiplicity 6, you'll get 6 distinct solutions here, each one with a higher power of t multiplying it. And those will all be solutions. So in other words, we have all the solutions that look like this, but that's really not necessarily k distinct solutions. But if we include the multiplicities, we'll get a total of k solutions, because each root counting its multiplicity will give you the right number of solutions, so that the total will be k here. And the same thing is true here. And I'm running out of space. I wanted to be able to write it all here, and I apologize for not being organized enough to make that work. Let me just erase some of this here so I can put it in. I'll erase this part here. So what if you have a complex number, a non-real complex number here, which is a solution? Let's say that these two are really identical, because S1 was the same as S2, so these don't give you two distinct solutions. So we can kind of cross that one out because it repeats the other one. Well, then we would have this coming from the root S1, which is lambda 1 plus I mu 1, being a root, as well as S1 bar as well. That would give you these two solutions. But if it's if S1 and thus S2 as well are multiplicity 2, you would also have solutions t e to the lambda 1 t cosine mu 1 t and t e to the lambda 1 t sine mu 1 t. It's just like before, you multiply them by t. If you have a complex root of multiplicity 4, you would have functions like this and this. You would have t times this and t times that. You would have t squared times this and t squared times that, and t cubed times this and t cubed times that. So you would have 4 total if 4 was the multiplicity, and that would be 4 pairs of functions this time, corresponding to a multiplicity 4 for S1 and multiplicity 4 for S1 bar. So there's a whole lot of stuff here. If you look at all the solutions I've written down, you'll see that if we started with an nth degree, an nth order, I should say, differential equation, you'll get an nth degree characteristic equation, which will have exactly n roots total when you count all the multiplicities. And if you look at all the solutions written down, you'll get exactly n solutions that we've written down when you include all the multiplicities. And here's something you'll just have to take, and you can verify this with some examples, and one can prove this in general. These n solutions, when you write it down the way we've done here, will in fact all be independent. In other words, the Wronskian of those n solutions will be non-zero, and thus all of those solutions, when taken together, will constitute a fundamental set of solutions to your differential equation.